Hi everyone, this video is a crash course for the beam brake sensor. It's going to cover how to hook one up and how to program one. So the crash courses are meant to be a very quick overview of how to do things. You'll probably, if you're actually wanting to follow along, you'll probably need to pause the video to make sure you can keep up, but it should be a good introduction for you to use this type of hardware. So let's start with that. So this is the sensor over here. It's a beam brake sensor, and it comes with an emitter and a receiver. So one of those two emits an infrared light, and the other will sense it. And if something comes between the two, in the gap between the sensor and the receiver, it's going to trip the sensor. So it's going to generate a different logic level. So that's the whole principle behind the sensor, is that something will come between the two elements and will trigger something electronically. We can also use the sensor either as a switch, so to just to detect if something does go in between the two things, or you can use it as a wheel encoder by having this wheel placed between the emitter and the receiver. And what that does, so if you have it like this and you have a drive shaft in there, and as it turns, you're going to get essentially the beam cut and then the beam allowed to go through, and you can count these the holes, essentially the holes and the non-holes, in order to tell how far this is turned. So it can either be used as a switch, where if you had something opaque, just cut the signal, or something, a wheel encoder, where you can have an encoder wheel. So the first step in using this is to hook it up. And in order to be able to hook it up, you have to know what the pins do. It's a little hard to see on this video, the clarity isn't perfect. But the first pin is labeled VCC, and that's your power. The second pin is labeled GND, or ground, so that has to be tied to ground. And after that, we have D0 and A0. And so D0 is the sensor's state. So if the slot is unobstructed, D0 should be low, or a 0 or a low. And if it is obstructed, so something is in the crack, then D0 will output a high, or logic 1. Uh, the fourth pin, the A0, is actually not used on this board. So there are 4 pins, but it's actually, in this orientation, just the left 3 that are used: VCC, ground, and then D0, so digital output. To use it on an Arduino, you're going to have to attach VCC to one of the VCC pins, ground to one of the ground pins, and then D0 to an input pin. All right, so now I've wired up the board just on the board side. So you can see I've put in, for D0, I've put an orange wire. Actually, I've got ground. It's typically what you want to do is you want to have VCC as red and ground as black, or in this case, I've got a darker color like gray or brown. So like that. So you've got a red VCC, in this case, a brown ground, and an orange D0. It really doesn't matter which colors you have, but if you always have, especially power, as the red one, it helps you make sure that you plug it in the right spot and don't fry the electronics. So on your Arduino, especially on this Elegoo board, they're all the red rails are power. They're typically 5 volts, some of them are 3.3. I believe this board is tolerant to both, but we're going to use a 5 volt rail. And since most of the pins are already used on this, the easiest one that is free is analog 0, so it's this blue one up there. So analog 0, 1, 2, and 3, I believe, are actually free, but you need to make sure that whatever you're plugging it into isn't used somewhere else. So do check your schematics or your instructions for that first. So in this case, we do have a power, a ground, and a 0 all next to each other. So we're just going to hook them up that way. So we're going to put in there is power, there's ground, and our orange, which is our signal, sorry if I'm blocking, is going to go here. Okay, so something like this. So that's enough to make this beam brake sensor work, just like that. So now that we have our hardware set up, so the board is plugged in, we need to write some code to make this work. Given we're just using it first as a beam break sensor, it's essentially coding it just like a switch. So we're going to into code. Let's create a new project. We're going to call it beam break. All right, and then we're going to go into this and delete. Let's delete most of this stuff. So clear the loop. You could just start from scratch. Actually, how about we do that? Let's just start from scratch. There you go. All right, so first thing we need to do is define which pin we're using. So I call it the encoder pin. We had it in A0. The robot I'm actually going to use this on that has the Elegoo Wi-Fi module on it, the SPO1, actually has it plugged into pin 3. 3 is actually used for something in Elegoo by default, but I have moved number 3 to another location so that I could use this pin. So let's call it 3 for this one, and understand that for you it probably won't be pin 3. All right, so first is our setup function. So these are the things we do once, and as we often do, we're going to do a serial begin, and we're going to give that a 115.2, so that's the baud rate of 115,200 bits per second to talk to our serial port. And then I like to put in a print line at the beginning of all my programs so I know that the program is running. So I will do something like beam break version 1, and then if I change my code, I might write version 2 so that I know that when I start the robot, if it still tells me it's version 1, then something didn't update the code. And I'm not trying to debug something that's actually, the problem is actually that the code didn't update. Next, we're going to have to pin mode, since this encoder pin needs to be an input, because we want to configure, in my case, pin 3 to read some value. Then in our loop, all we're going to do is get that pin value and then print it to the screen. So we can do that in one step, but since we're likely going to use that pin value somewhere else in the code, let's actually do a digital. So we'll do an int or even maybe a bool and say digital read. And then again, the encoder pin. Sorry, that was wrong. Bool. And we're going to call it value equals digital encoder. All right, so now we're reading that and we're storing that in value. And then we're just going to go serial dot print line, and we're going to print that value. And then I'm going to delay, let's say 100 milliseconds, so a tenth of a second, just so it doesn't overwhelm the serial port. If all we're doing here is printing the serial port as fast as we can, it's going to maybe overwhelm our serial port. So I'm just going to give it a bit of a break, and we're going to get 10 values per second. So the next step now will be to upload that code. So we're going to configure this to be the right board and the right port. And then we're going to possibly verify the code first, which we can do now, just to make sure I didn't make any typos. Happens to the best of us. Oh, I didn't even choose my compile server. I should probably do that first. We want the WWFIRST Arduino app server. It's going to be an Arduino, and let me turn the other robot on. It might get there in time. It's going to be TCP to Elegoo.local. All right, so now let's go back to the code. And let's build it. There you go, it's compiling. Now let's take a chance to see if this is connected already. We can also use this one here. Compiling, uploading. Device not responding. Okay, so I need to hook up my robot, so I will do that and be right back. All right, now that I plugged in my wireless module correctly, or more completely, and I selected the TCP to Elegoo.local at the bottom, hit program, and we actually have the appropriate successful programming. So now if I go to monitor, I can see that the status of my pin or my sensor is 0. And then if I go to change it, it goes to 1 or 0, whether I block it or not. All right, so that was a pretty simple way to use the beam break sensor as essentially a limit switch or some kind of trigger for when something moves to a certain spot. But what's probably most commonly used for this is the wheel encoder. And to do that, you're going to have to retrofit your robot with the encoders. So it takes a few steps. You will need to take this 3D printed part, which was part of your kit of parts, and you'll need 2 of these. These are um, little, um, essentially little shims for your motors to give space for the wheel encoders. Because if you try to put the wheel encoders on the motors back there, you'll find that they're down too low. They'll hit the plate. So we're going to put these little shims right here where the motors are, where that aluminum block is, to raise the motor up so that there's enough room for the wheel. That part requires you to first, well, actually most of this requires you first take off the 6 screws at the top, which I've already done. So now you can pull that off. The next thing you need to do is actually slip these sensors inside this. So you want to slip them like that, such that where there's an angle, that's where the pins come out. So you want these things will be going in far so that they reach the drive shaft, but under this plate. So this is all going under this plate here. This robot already has this on here, so I'm going to take that out of here, put that aside. So essentially, when you unscrew this, you'll need to also unscrew uh, the two screws holding your battery in, and then you'll put in that 3D printed part, then slip in your encoders. So this one here would go through here and up through here. And then you need to add those shims over here. So you're going to have to unscrew these motor mounts screws, raise that up, put this under essentially here, but on the other side, and screw it all back together. The wheel encoders, these guys, the discs need to go on the end of the shaft, and you want them as far this way as possible. So it helps a little bit if you have this bump going towards the motor, lets you pull it out a little further, because you'll find that these things are very close to the center. If you push the wheels all the way in, they're never going to fit here. So you have to pull them out so they can fit here, if you can see that. Okay, so the wheel should fit right in the U over there. So it's hard to see with the angle and with the black. Everything black is hard to film. So there, one here, sensor here, put it all together, put that in, put your 6 screws back, and then you're good to go. You can actually test these encoders once they're plugged in. If you turn them on, they have a light. So if you do put something in, they'll flash. So you can tell that they're working even if you have no code attached. Those lights are hardware. They're not software driven. So all right, so I'm going to go ahead and put this back together so we can write code for the wheel encoder part. All right, so first of all, I increased the font size. Hopefully it makes it a little easier to read. If you wanted to see the previous program bigger, hit pause now. Otherwise, we're going to clear up some values. We're going to keep the setup, so just delete that, and move on to what we need to do for an encoder for the wheels. All right, so first of all, we still need to define which pin we're coming through, and that hasn't changed, whether I'm using it as a switch or as a wheel encoder. I've left it in the same pin, pin 3 for me. The setup is the same. I'm going to set up the serial port to run at essentially the fastest practical speed, but instead of beam break, I'm going to call this wheel encoder. And this program only does one side of the drivetrain. If you wanted to read both sensors, you would just do the same thing, but duplicate it. So you would read the left and the right, which is useful if you want to know if your robot's drifting one side or the other, if it's one motor's maybe not pushing as fast as the other, or in order to turn, when you want to turn, it's good to know what your wheels are doing separately. All right, so we still have to set this up as an input, so that's the same. And then essentially what we're going to do, the important part for this is you're needing to keep track of how many ticks or holes and non-holes that you're going through. So in order to do that, you would want to go and set up maybe a couple of global variables. I'm going to call one int encoder ticks. I'm going to initialize that to 0. And then um, we're going to go in here and we're just going to say if my digital read encoder pin, because the theory, what we want to do is we're going to say, I'm going to read it, and if it's not the same as it was when I read last time, then we've got something that's changed, and we want to count that. So I'm going to say, and so let's actually grab another global variable here. I'm going to call it a Boolean because it's either high or low, so I'm going to call that last encoder state. I'm going to assume it's false. I really don't know what it is at the beginning, but if we miss one tick, it shouldn't make a big difference. So I'm going to say if my digital read, so I'm saying if the pin's current state, so I'm getting the pin's current state, and if you prefer to have that separate, we can separate that, I'll do both. So if my current state is not equal to my last encoder state, then I want to count. So this is where I'm going to go encoder ticks plus plus. Okay, so that'll let me count the encoder ticks. I could have, if you don't like having it all in one line, I could actually say bool current state equals, and just move this, cut that out, paste it in here like that, and then current state equals that. Okay, so if you're going to use it more than one, if you're going to use current state in more than one spot, this may be a better way to do it. Otherwise, you can just insert it there if you're going to use it once. All right. Also, because we're kind of running a little practice code here, I'm also going to do a serial dot println encoder ticks. Okay, and that's just so essentially anytime the value changes, I'm going to print it to the monitor. This is not something you want to do with your live robot once you're done, because printing to the monitor takes quite a bit of time, and that might cause the rest of your program not to run fast enough. But as a debugging thing, this is actually quite good. All right, so I think that's all. So first let's compile and see if I've made any typos or obvious mistakes. Done, good. And then let's go to the next step and upload it. I think the robot is on. Yes, it is. And you may notice I switched robots on you because that's the one that's got the boards all wired up. And it's giving me an error here, so let me go check that I actually turned it on. All right, so that took 2 tries to get done. I reselected the port down here, and that seemed to have cleared it up. So now the program is running, and if we go to the monitor, we should be getting, actually we should not be getting that. That's quite the numbers go and fly. So let me have so it thinks it's actually moving. So I've obviously made a mistake. So let's go have a look at that. And if we look at the code, so program, close that. So if the current state's not equal to that, we increase the ticks and then we print. Oh, yes, that's if you don't update your encoder state from the last time, it's going to be problematic. So if you've spotted that ahead of time, good for you. So the very first thing is if you're checking a state, make sure you update the state so that the next time you go through, it actually works. So like that. Sorry, no. Yeah, so you can do this multiple ways. That's probably like the cleanest. You could also say, since we're toggling, you could say that the current state is equal to not last encoder state. So this is making that last encoder state toggle. Or you could also just assign it to the current state and then next time when you check, it'll actually have flipped. So the problem with not having this is that it's going to be wrong all the time until it's either always going to be wrong or always not going to be wrong. So anyways, not what you want. So let's see if it'll work on the first try here again. It does take a few seconds. Yes, that worked. All right, so now let's look at the monitor. Excellent. So it says wheel encoder version 1, and it counted 1 tick, so meaning it wasn't on what it was originally. So now if I look and I turn, I think it's actually the right wheel that's connected. Let's see. Yep, there we go. So as I turn the wheel, you can see the ticks go up. And you can determine how many ticks it takes to do a full wheel revolution, and then you can start doing math and figuring out, okay, if I turn a whole wheel revolution and my diameter is so many centimeters, that means there's a wheel circumference of times pi of that. And you can essentially say, all right, 490 ticks is equal to 1 meter, and then you can make your robot move automated bits. So if you want to move half a meter, you move 240 ticks, for example. And you can have in your code just set the target ticks to be 240, and then keep checking your tick count up here. Check this variable, and when it hits the amount of ticks you want, then you can stop. Okay, so those are the basics of using wheel encoders for drive auto. And as I said, that was only for one side. And the other thing that if we go back to the serial monitor, it's maybe hard to tell, but if I turn clockwise, so I go from here to here, or if I go from here to here, the counts always keep ticking up because we don't have an encoder that can read direction. Okay, it's not a quadrature encoder, it's a single pin encoder, so it always counts up. So in order for you to compensate for that, every time you change your motors from going forward to going backwards, you'd have to set some kind of variable somewhere that would have to say something like bool going forward, something like that. And then somewhere else in your code when you're doing the motors, wherever that is, um, motors, you would have to, every time you flip it from forward to backwards, you would have to change that, sorry, going forward variable to whatever direction you're going. So let's say here we switch to going backwards, then we would have to say, you wouldn't do this in a loop like this, but whatever. You would say false. And then instead of just blindly incrementing, in here you would have to say if going forward, we would increment, else we would decrement. Okay, so if we actually had that, because we know what we're doing with our wheels. So if we're telling it to go forward, set this variable to say going forward, and then you know to increment your ticks. And then when you're going backwards, set that to false, and then you're going to be decrementing your ticks. So that's one way to tell where you're going kind of in absolute terms. So often you may not care. You're going to do a motion. So if it's forward a meter or backwards a meter, just set the motor, reset your ticks, and just count them. You'll be good to go. But if you do need to compensate for the robot going forward and backwards, then you can use this kind of logic. The alternative is to use a quadrature encoder, which is, we do have one that's kind of like a knob turning one, which does have the ability to count the direction. So that's about it. It's a quick little 25-minute intro to this kind of hardware. If you have any questions, post it on our Discord channel or go online. You can read about encoders. Hope this was helpful, and there will be more similar videos for the other pieces of hardware.